from the Center for Accident and Precision Physics Research. Today's colloquium is going to be given by Professor Paul Debevec. He's from the University of Illinois, Urbana-Champaign. I know Professor Debevec from more than 20 years now, and I know him in the context of the new G-2 experiment as a collaborator of one professor that really understands the equations before he writes them over, and he really checks them thoroughly. So if we want our papers to be correct, we send them to him to check over all the equations as applied to the particular circumstances. So he pays attention to the details. Professor Debevec also told me some time ago that he's interested in the energy crisis and climate change crisis, how these things are connected to the fact that the solutions are not easy. So in the middle of this pandemic, why would we have another talk on the potential thing that could come a little later? Well, I remember I used to hear things and warnings about the virus that could come and really wreak havoc to societies around the globe. But, you know, because it never happened, it was unreal, and we never paid too much attention to it, and some of the countries are not doing as well. And the climate change crisis may even be a bigger crisis later on. So it's good to know the facts. Usually the generals always fight the old war. Let's be prepared for the new challenges that come along. So we need to be informed all the time. Professor Paul Debevec, he did his undergraduate studies at MIT. Then he went on to Princeton for master's and PhD, and that's PhD in 1972. And he became a professor at the University of Illinois, where he was for a long time, and now he's a professor emeritus. And Professor Debevec asked me to request the talks because of the Zoom format, the questions, to leave them for the end. You can also email to him, and you don't have his email address, please ask. Okay, the energy needs of the planet and the climate change challenge. Professor Debevec?
Well, thank you very much. I must thank my colleague Yanis for this invitation. I've had the pleasure and privilege of working with him on G-2 for quite a few years, but this talk is nothing about muons. It's about climate change and the energy needs of the planet. And I've prepared hopefully about 50 minutes of presentation, but if I don't quite get the timing correct, I blame it on the international date line. So here I am, just south of Chicago, and there you all are just south of Seoul. We're over 10,000 kilometers apart, but still we could try to share with each other some thoughts about climate and energy. So here's my outline. I'll start with extreme weather and talk about climate science. I have to remind you that I'm a physicist. I have no credentials in climate science. I only know enough to be dangerous. but I'll move on to global energy. I'll talk about international efforts, non-fossil fuel, a few words about what if the transition is too slow, and then a quick one-slide summary. So here we go. Extreme weather. So every year in the bulletin of the American Meteorological Society, there's a map of extreme weather events, and this is last year's map. It's 2019, and there's too many words on this map for you to read them, but what I hope that you're impressed about is that extreme weather events are throughout the globe. And in fact, if we look at what was on that map, Africa, the third warmest year, Alaska, the warmest year, Arctic sea ice, the second smallest, Asia, third warmest year, Australia, the warmest year, cyclones of massive wind speeds in Mozambique, Arabia Sea, typhoons, hurricanes, and in my own area, the United States Midwest, massive flooding. So extreme weather is with us already. And in fact, it's with Korea. Here's a list of recent and possibly future climate change impacted Korea. You suffer persistent smog. Your average temperature is actually higher than the global average. Your summers now are more than 30 days longer. You had severe heat waves already. You have stronger typhoons. And just as my California, United States, you have severe wildfires and very heavy rainfall. So we have seen the effects of climate change already in extreme weather. In fact, just a few weeks ago, the World Meteorological Organization put out a news release saying that there's a 20% chance that one of the next 5 years will already be 1.5 degrees warmer than pre-industrial levels. And we'll come back to this 1.5 degrees. It in fact is one of the goals of the Climate Change Convention, to stay below that. So let's talk about climate science for a while. It's quite a complicated subject, but I'll try to give the basics of it. So here's a picture of the energy balance between the incoming solar radiation and the Earth. And if you look at the upper atmosphere, there's 342 watts per meter squared coming in, reflected sunlight, 107 watts per meter squared, and infrared escaping from space, 235 watts per meter squared. So if you do the arithmetic, the incoming radiation and the outgoing radiation completely balance. In fact, if you look at the level of the Earth, the incoming radiation from the sun, the infrared radiation emitted by the Earth, the infrared radiation absorbed by the Earth from the clouds, and convection from the Earth, they also balance. And then this third layer here, which is called the atmosphere or the clouds, also the energy balances. Incoming sunlight, infrared emitted to space and back to the Earth. So here is the Earth that is in balance. And it's in balance with an average solar irradiance of 342 watts per meter squared. Now here's quite a complicated picture. This is the balance of the carbon cycle. And there are numbers that are in black, and there are numbers that are in red. So the black numbers are the pre-industrial steady state. And the reservoir size are in gigatons of carbon. So in the atmosphere, before industrialization, let's say roughly beginning early 1800s, there were not quite 600 gigatons of carbon. And through industrialization, human activity, there's now 165 extra gigatons of carbon. And this carbon is exchanged through vegetation, emitted by fossil fuels, exchanged in the ocean. But the carbon that's in the atmosphere is increasing because of this continually burning of fossil fuels. And indeed, the concentration of carbon dioxide in the atmosphere is known. Here is one of the sites where it is measured on the top of Mauna Loa Observatory in Hawaii. It's called the Keeling curve. And I must proudly tell you that Keeling, in fact, was a graduate of the University of Illinois. And starting way back in 1960, he began very accurate measurements of carbon dioxide concentration. And this sawtooth structure, this is in fact the biosphere that is breathing. Every spring, more and more carbon dioxide is taken out of the atmosphere as plants grow. And then in the fall, as plants decay, it goes back into the atmosphere. What we see here is an inexorable rise of carbon dioxide. Pre-industrial times were 280 parts per million, and now we are about 415 parts per million. So that carbon dioxide excess mostly has come from fossil fuels and industry. Some from change of land use, because when you convert some land to crops, the carbon dioxide leaves the soil. But carbon dioxide could also go back into the soil, it can go into the atmosphere, and it can go into the ocean. So here in 2015, the carbon dioxide flux is now something like 40 gigatons per year. It is difficult to fathom how much a gigaton of carbon dioxide is, or a gigaton of carbon happens to be. And we grapple with these enormous numbers. Now, this imbalance of carbon dioxide, which traps heat, causes a change in the energy balance. And that change of the energy balance in climate science is called a forcing. And there are a number of sources of the forcing. So here we see in gray carbon dioxide. More carbon dioxide in the atmosphere, in fact, produces a forcing not quite 2 watts per meter squared. Now remember, the sun is bringing in 342 watts per meter squared. So the energy imbalance is at the 1% level, a few watts per meter squared. But if you continue to put energy into a system, its temperature has to rise. The dotted red line is the total anthropogenic, that means human-caused, effective radiating forcing. And again, I'll point out to you that that's about 2 watts per meter squared. Now, it's a complicated mix of positive and negative. For example, aerosols. Aerosols tend to, in fact, reflect sunlight, and that's a negative forcing. But all in all, the radiative forcing is positive, about 2 watts per meter squared, and almost completely caused by carbon dioxide and other greenhouse gases. So variation from the sun. Yes, there is some variation in the sun, but it's tiny. Variation from volcanic eruptions. I didn't point out here, these spikes here, each time represent a volcano. And a volcano throws aerosols into the air, reflecting sunlight, and indeed that's a negative forcing. More about that later. But here it is, human-caused radiative forcings at the level of about 2 watts per meter squared, and that's what's heating the Earth. And again, that forcing is due to greenhouse gases, mostly but not exclusively carbon dioxide. Now here are the analysis of temperature records from 1880 to the present. There are 5 different groups represented here. They do this quite complicated global averaging of temperature, and these 5 different efforts of producing the global average temperature largely agree. And this is called the temperature anomaly because we choose arbitrarily some period and draw a line. And that period here is 1950 to 1980. And since that time, since 1980, the temperature has gone up now almost a degree centigrade. Notice that there are considerable variations in the temperature rise. And indeed, here's a period from about 2005 for almost a decade where it did not appear that the temperature was going up at all. But looking at the trend, temperature is going up. Pardon. So how do we know that that temperature rise is due to human influences? And we know that from climate models. So the black here shows the observed temperature rise, and each of these lines represents from a climate model all natural drivers, volcanoes, solar, and orbital. So these are natural influences, and they do not, in fact, account for the observed rise. So here's human influences. And way up here is greenhouse gas, which in fact has the effect of raising temperature. But aerosols, in fact, have the effect of lowering temperature. But if you put the positive and negative effects together, you see that the observed temperature rise is largely accounted for by human drivers. So you put all drivers together, and agreement with observation is really quite good. So here is a picture from 1970 to not quite 2020. And all of these lines here represent the fluctuations in the temperature record from a number of different analyses. This big band here in gray represents the compilation of some 30 to 40 different climate models. And these climate models, in fact, are run and checked against one another in a consortium. And you see largely that the envelope, in fact, accounts for the observation. So I think there is confidence that climate models have quite a bit of accuracy. So now we have to extrapolate. But when you extrapolate, you have to make an assumption about emissions. And the assumption that's made in this extrapolation that emissions will, by the year 2100, double. So we'll go from the 280 pre-industrial to 560, and there the temperature rise will be roughly 2 degrees. And that doubling of CO2 and the temperature rise that occurs is known as the climate sensitivity. Here is basically the simple message of climate science. Cumulative CO2 in the atmosphere on the horizontal axis, temperature rise on the vertical axis, straight line through different CO2 concentrations. So more carbon dioxide in the atmosphere, higher temperature rise, and the result is really quite linear. One of the goals of the UN Climate Change Convention is to stay below 2 degrees, and we're basically halfway there, both in temperature rise and how much carbon we can let go into the atmosphere. Very recently, in fact, just a week ago, an enormous review paper was published in Reviews of Geophysics, a review of climate models and data over the review took about 4 years to compile. And what this review has the message, this red line here is the probability density for the temperature rise, assuming a doubling of CO2. Again, that's 280 to 560 ppm. And you see that that probability distribution actually had quite an enormous spread. And with some significant probability, the temperature rise could be rather low. However, this new paper by Sherwood et al. Basically says no. Lower temperature rises, in fact, are not very probable. And this is not good news. So climate sensitivity, which for decades has been rather uncertain, this new research, in fact, has narrowed the uncertainty, and it narrowed the uncertainty in the direction that low temperature rise is much less probable. So where does the CO2 come from? I think we all know. Here's a picture of the United States. And on the left are sources of energy, primary energy. And they are oil, natural gas, coal, renewables, and nuclear. On the right are places that the energy is used, and those are divided into transportation, industrial, residential, and commercial, which are largely buildings. In intermediate, these primary energy sources can be converted to electricity. And each of these arrows, in fact, shows the route between source and use. And again, the numbers are too small to read, but the message is actually pretty clear. For petroleum, it mostly goes into transportation. For coal, it dominantly goes into producing electricity. Natural gas goes, in fact, many, many different places. Nuclear energy produces electricity. So that's the United States. In the United States right now, in 2018, we still, in fact, from our primary energy, obtain it 80% from fossil fuels. Renewables are about 12%, nuclear is about 8%, and of this renewables, about half of that is hydroelectric power. Is the United States unique? Answer, no. Oh, let me sneak this in first. We're going to talk about moving away from fossil fuels. So what are the possibilities? Well, for transportation, you could go to biofuels, you could go to electricity, or you could go to hydrogen. There are 3 possibilities. We all know about electric cars. We all know about fuels like ethanol. For electricity, hydro, in fact, is already used, but the possibilities of photovoltaic, wind, biomass, geothermal, or nuclear power. For industry and buildings, we have to figure out substitutes for space and water heating and for lighting and for many, many more uses. So there are considerable possibilities moving away from fossil fuels. So I asked the question, is the United States unique? Answer, no. Here's a similar plot for the world in 2018. And in the world, about 85% of primary energy was obtained from fossil fuels. If you look carefully at the slides, and I'll post them, you notice that the units here are quads, 10 to the 15th BTU. And I, as a physicist, have not much good to say about the unit of a quad, but in the United States, we use about 100 of them. So it's easy to take percentages. So the United States is not unique compared to the world. In fact, here's the same kind of plot made for Korea. In Korea, 82% of the primary energy is derived from fossil fuels. A little bit more from coal, a little bit less from natural gas, a significant amount of nuclear power. Renewables in Korea have just not taken off much at all. But still, the message is that as the United States and the world, there's an overwhelming dependence upon fossil fuels. Now, there is, in fact, a movement away from coal to natural gas in the United States and in Korea and in many other places. And the reason for that is coal is dominantly carbon. You burn the carbon and you get CO2. Natural gas is dominantly methane. And when you burn the methane, yes, you get CO2, but that hydrogen produces water. So for the same thermal energy production, natural gas produces half the CO2. So movement from coal to natural gas is a benefit, but natural gas is still a fossil fuel. It still produces CO2. Here's the energy flow that I tried to make up for Korea. And just as in the United States, petroleum dominantly goes into transportation. Coal goes into electricity production. A considerable amount of natural gas goes into electricity production. But natural gas, in fact, goes a little bit everywhere. And of course, nuclear power produces electricity. So here from 1960 to the present are emissions, and you see coal and oil and natural gas. Coal is tapering off a bit. Natural gas is rising. Oil is also rising. Basically, the consumption of fossil fuels has not slowed down. Interestingly here, cement production is a non-negligible part of CO2 production. And this is in fact quite a technical challenge. I mean, all construction depends upon cement. And right now, the process of making cement produces lots of carbon dioxide. So let me talk a moment about United Nations Framework Convention on Climate Change and the Intergovernmental Panel on Climate Change. These are two international efforts under the auspices of the UN. So the framework was in fact ratified in 1992, and from Article 2 in the framework, it says that stabilize greenhouse gas concentrations in the atmosphere at a level that would prevent a dangerous anthropogenic influence with the climate system. So 197 countries have ratified this convention, and its goal is to stabilize greenhouse gases at a low enough level that we won't change the climate. So the convention produced a series of conferences. They're called Conferences of the Parties, and they've gone on since 1995. Most important of the conferences was in '97, which produced the Kyoto Protocol, which shamefully the United States, in fact, never ratified. In 2009, it was the first time that a definite goal for temperature rise was promulgated, and that was at Copenhagen, and that's the 2 degrees temperature rise. Why 2 degrees? And basically 2 degrees, the Earth has not seen 2 degrees in many millions of years. The most important conference happened 5 years ago in Paris. It produced the Paris Accord. The goal of the Paris Accord was to well below 2 degrees, 1.5 degrees. And those conferences have continued year after year after year. The conference this year, in fact, was delayed because of the pandemic. So I'll speak mostly about the Paris conference. But first, the IPCC. So this is a group of scientists. They themselves do no original research. Their goal is to review research and produce a review, a synthesis. And starting with the first review, 1990, they said the unequivocal detection of enhanced greenhouse effect is not likely for a decade or more. But in 1995, there's a discernible human influence. In 2001, the human influence is likely. In 2007, the influence is very likely. In 2014, it is extremely likely. And the next report will be in 2021. And frankly, I don't know what you can do beyond extremely likely. And why has this increased certainty happened? Well, we've understood the climate much better. The climate models have greatly improved. There's considerable amount of data from satellites and other places. So now, quickly, the Paris Agreement is voluntary. So every sovereign state has to act as itself. And they act for political reasons, self-interest, public pressure, reputation. There is no enforcement mechanism in the Paris Agreement. This is what we have. And the key points were to each country make a pledge, a nationally determined contribution. And those pledges would be reviewed. In fact, the review, in fact, is coming up for the pledges that were made in 2015. Now, just in the last few months, a group of 9 NGOs and 2 international laboratories claims that they will be able, with satellite data, to track real-time atmospheric carbon emissions from various individual sources. Frankly, I'm amazed. It is a big background and it is a small signal. But if this would happen, all the disputes about emissions would in fact disappear because there would be a real-time measurement. Let's hope that this consortium in fact could pull it off. So here's the map that shows the different pledges across the world. And in black, the pledge is critically insufficient to obtain the climate goal. And there's my own country, the United States. In fact, we are the only country that has said that it will withdraw from the Paris Agreement. And I have to tell you, it's not my fault. So 2 degrees compatible, a few countries. Insufficient, in fact, almost all the industrialized world. So these pledges, in fact, really are insufficient, but they're all we have. Right now, the pledges will probably produce something like a 3-degree rise. And I remind you that with a 1-degree rise, we are already seeing extreme weather. 3 degrees is extremely serious. So by 2100, the rise might be 3 degrees, 4 degrees. It could be quite bad. So the last meeting, so there are some brighter spots. Right now, there are many countries that say by 2050, they'll zero out carbon emissions. Well, at least they have a goal. Do they have a plan that, in fact, will achieve this? That's quite another matter. And in fact, Korea, with the new election, has also put forward plans to go to renewable energies and to zero out emissions by 2050. So that's good news also. Just last year, there was an international strike by young people. And I have to show you this next slide. There, in front of the Swedish Parliament building, is a young woman, almost a girl, with a sign in Swedish that says, "Strike for climate," school strike for climate. There she is alone in August of 2018. And of course, this is Greta Thunberg. Just a year later, in 50 cities, there are massive demonstrations for climate change. Do something about climate change. And indeed, there was such a demonstration in Seoul. So the enormous number of people are screaming that something has to be done. And that's good. So how do we move away from fossil fuels? And I show this slide because here, the greatest renewable non-fossil fuel resource by far is the sun. So right now, the average power demand globally is 21 terawatts, and by 2050, it'll rise to 30 terawatts. So there's the sun. There's wind, significant. Biomass, hydro, not so much. But where the real enormous amount of energy is from the sun. We're not going to run out of fossil fuels. There's ample coal left, lots of oil, lots of natural gas, and quite a bit of uranium. There's probably 400 years of coal at present usage. And I think I showed this slide already, giving options for non-fossil fuels. Now I remember why I said this. So nuclear power. Nuclear power is not carbon dioxide emitting. That's not a fossil fuel. The world has considerable nuclear power. Korea, in fact, much more than the average. However, nuclear power has massive opposition in Korea, in Europe, in the United States. I would not, in fact, be optimistic about nuclear power. So what about the sun? Here's the United States. Our Southwest, in fact, has enormous solar power resources. And with the same color scheme, here's Korea. So there are quite a few places where the solar resource in Korea is extensive. Wind power. So in the United States, our Midwestern or Central Plains, enormous wind resource. Offshore, in fact, is quite considerable. In Korea, not as good, but offshore resource is in fact quite significant. So Korea has both solar and wind resources. So why don't we have all renewables already? And the answer is there are problems. So there's the cost, something I call the area, variability and intermittency. And now I see I better start moving a little faster. So here's the cost of different fossil fuel options, different renewable options. And right now, natural gas is the lowest. But renewables aren't so bad. But this is the total cost. If you look at capital cost, I mean, what does it cost actually to produce a power plant? Natural gas is still by far the cheapest. Renewables not so bad in many cases, but the outlay for building renewables is much more expensive. Now the area problem. So if you just take the consumption of a country and divide by its area, you get a power consumption per unit area. And Korea, in fact, has quite a high power consumption per unit area, considerably more than the United States or Europe. And that has the problem. So here's population density, here's energy consumption, here's Korea, and each of these lines represents the power per unit area that can be produced by a given technology. So energy crops, only 0.5 watt per meter squared. Wind, 2.5. Solar, maybe 5. So sadly, Korea has the difficulty that its power consumption is quite challenging compared to what's available from the renewables. So I call that the area problem. Then there's the variability problem. So in blue, this is in my own locale, wind power. In orange or yellow, solar power. You see day after day after day, and you'll notice that there are times when there's no wind and there's no sun. So wind and solar are both variable and intermittent. And there's actually quite a nice paper that analyzed the problem of intermittency and wind power in the United States. I'm going to have to skip through this because I don't want to run over. This group, in fact, takes 30 years of climate data, so that's wind and solar, all over the United States, and comes up with the fact that if you want to keep reliability at the level of 99%, you have to have significant number of days of storage. And right now, there is no storage. So the other matter is the infrastructure. Here's a quote from November 2000. Holdren was the advisor to President Obama. And he says that the world energy system of fossil fuels is perhaps worth $10 trillion. It has a natural turnover time of 20 to 50 years. So there's an enormous inertia from the infrastructure of fossil fuels. So there are possibilities to get away from fossil fuels, but it is indeed a challenge, many challenges. So what if the transition away from fossil fuels is too slow? What if the temperature it creeps up higher and higher with more extreme weather? Are there possibilities? Yes, but the two possibilities go under the names solar radiation management and carbon dioxide removal. So let's talk about carbon dioxide removal just briefly. Would it be possible to take carbon dioxide out of the air? Yes. There certainly are physical chemical processes that you could capture CO2 from the air. But right now, it is extremely expensive. Once you capture the CO2, could you store it geologically? And the answer to that is yes. That's extremely well proven. So CO2 removal, possible, but extremely challenging. Solar radiation management. In fact, nature has shown us that that works. So in 1991, there was an eruption in Chile, Mount Pinatubo. This is just within hours of the eruption, you'll notice an enormous cloud of aerosols. So into the atmosphere is spewed gigatons of sulfur dioxide aerosols. And here, after the eruption, is global temperature. And then you see from that volcanic eruption, global temperature went down 0.6 of a degree. So should you want to, you could throw massive amounts of aerosols into the atmosphere, block out some of the sun, and lower the Earth's temperature. This is, in fact, possible. It's actually not so expensive. It might cost $20, $30 billion. Not so expensive. It could even be done by a single country. But clearly, the danger of doing this experiment on the globe is significant. Is it mad? Well, maybe it's mad. But living with a temperature rise of 2 or 3 or 4 degrees might be also insane. Here is a, if you want, artist representation from Carbon Engineering. They're one of the companies that is championing the idea of CO2 capture. There's a truck, and that shows you the scale of this. So this device here is set up to gather up air, takes the air, puts it through chemical means, removing the CO2, which then has to sequester. But as you can see, you need massive devices to do this. And the expense right now is probably a few $100s per ton of CO2. So here's a summary. I went quickly. I'm happy to try to address any matters I went too quickly over. So I tried to show you that already there's a 1 degree temperature rise, and it has produced extreme weather. And I showed climate science shows that there's a link between greenhouse gas emissions and climate change. It is now incontrovertible. So the goal of the Framework Convention is a 2 degree rise. It would be prudent, but keeping the 2 degrees, it looks difficult. And I'm being generous here, saying that international efforts struggle. Perhaps national and local efforts which have begun will be successful. We can hope. So there are non-fossil fuel options. They have challenges. Could you run a country on 100% renewables? Yes, probably. And each country is going to be a little different. To me, the biggest challenge is the absolutely entrenched economic and political infrastructure. Solar radiation management is possible, and I'm being generous here. I say not advisable. Carbon dioxide removal technologies, to me, they still are quite fanciful. I try to distinguish between technologies that only need a breakthrough and those that need a miracle. And I think carbon dioxide removal needs a miracle. Well, thanks very much. I'll stop sharing my screen, and I'm willing to try to answer questions. I'm sure that Giannis will moderate.
Okay, let's have questions. Maybe you can speak.
Hello.
Hello?
I'm not. Let me try again. I'm not sure I heard the question.
I didn't hear anything.
Oh, okay. Well, I do have to confess it's a lot of material to be thrown at someone in 50 minutes. My email is debevec@illinois.edu. I'd be very happy to answer any emails. And when I post the slides, there are no secrets in what I presented. You know, everything I have citations for, and you know, you could pursue these matters. And I wish the best to all of you.
You're not done yet. No.
Okay, we're not done yet.
Right. Any questions?
I would like to raise a comment, if I may.
Please. Yes.
I'm the director of the IBS Center for Climate Physics. And so I've also been a lead author on the 5th assessment report of the IPCC. I just
Oh my
wanted to
goodness.
make one comment, and that is referring mostly to your first slides, where you essentially assemble all the climate extremes and you argue that this is a good sign for well, the influence of humans on the climate system. So for heat waves, that is absolutely correct, but one has to be very, very careful including tropical storms, cyclones, hurricanes in that statistics. Number one, we don't have very long, accurate records of tropical cyclones and hurricanes that go back long enough to do this attribution part. So we can do detection. We see trends in certain areas. The number of strong tropical cyclones and hurricanes is increasing in certain areas. In other areas, it is decreasing. So it's much more complicated. So we can see changes, trends are there, but to uniquely attribute them to human activities is a completely different scientific challenge. So there I would be very careful. In fact, we just submitted a paper arguing that the detection of the human influence on tropical cyclones would take much longer, maybe another 30 to 40 years. So we are still in the noise when it comes to extreme storms. When it comes to extreme events, I think everything you're saying is absolutely correct, but just be a little bit careful. The atmosphere is a very noisy system, in particular when you go to regional scales.
I have to thank you for your comment. You are completely correct. Human attribution, there's actually every year an analysis that's published in Bulletin of American Meteorological Society, trying to do this matter of human attribution. And indeed, as you point out, the typhoon, cyclones are among the issues that are difficult. Still, the winds, the maximum winds are impressive now. Mm-hmm. They are truly impressive. But you know, your comment that the climate system is complicated, I'll tell you a physics story. One of the theorists that I know rather well, John Nageli, he's at MIT. He does lattice gauge calculations. One of his best graduate students who had done a lattice gauge calculation decided rather than to go into that area of research, he went into climate science, and he told John Naegeli, you know, lattice gauge actually is pretty simple.
I also worked on quantum chromodynamics before, so I know what you're
So you agree? You agree? Okay.
I agree, yeah.
That's right. Very good. So, looking at the whole picture, Paul, what is your prediction? From my point of view, human beings don't do anything unless they have to. And as you said, the economic and political questions are very surmountable. Those are very difficult to overcome. So do you have hope we'll be able to understand what to do?
So I wish I could be optimistic. What heartens me is the younger people are much more aware and concerned. Now, if we could ever get them out to vote, because the political system, you know, right now, nobody makes any money taking carbon dioxide out of the atmosphere. Indeed, it's completely the opposite. You make money putting carbon dioxide into the atmosphere. So it's the massive failure of the market system. A carbon tax, a serious carbon tax, could change, not quickly, but in the matter of a decade. But we have to realize that there will be trillions of dollars of stranded assets, coal and oil and natural gas, that will have to stay in the ground. And that just has to happen. I think that a dramatic change of the political system will not happen until things sadly get somewhat worse. I think the idea of solar resource radiation management is scary beyond belief. But if there were a breakthrough in storage, we could in fact do the transportation system right now. We know how to make electric vehicles. We could make hydrogen and have fuel cell cars. Biofuels, maybe not. Maybe biofuels for airplanes, but transportation, straightforward. Electricity generation. There is indeed the problem of the area. So, but right now, there are technologies for multi-gigawatt transmission, high voltage DC lines. So countries like the United States, Europe, in Europe, they could depend upon North Africa's sun for energy. So the storage problem, in fact, needs to have a breakthrough. I don't think it needs a miracle. And then, as much as we could electrify, we should do it. Industry, I have to say, is complicated, and you know, some industries, I don't know that anyone has a way to figure out how to decarbonize them, but people are thinking about it. So my summary answer to you is, sadly, I think things are going to get a little worse. But I think the pressure for change is there. I think the possibility for some breakthroughs are there. Certainly, the technology for capturing the sun and capturing wind is highly developed. That's as best as I can predict. sadly, it will be a world that I will not see at my age. I hope for it the best.
Okay, well, as usual, the young people have the hope, so we'll take that encouraging note. And thank you very much, Professor Debevec, for the wonderful colloquium. And this colloquium has been recorded and it will become available on our website. So,
I thank you all, and it's been a pleasure. Good night.
thank you. Good night. Good day to on this side.